surface functionalization. We make devices, we make systems where we want to detect certain things. Maybe they are chemical species, maybe they are biological molecules, maybe that's some toxic material in water, maybe it's just gas leakage. Whatever we do, we have to make our devices to detect specific targets, specific target molecules. We make our surfaces functionalized with some sort of layers, some sort of maybe molecules or chemicals or coatings that can bound, that can detect and bind to those species specifically. So the keyword here is specifically, specifically or selectively. These are two words which we use alternatively. What does it mean is that if I recognition, it simply means it's molecular recognition. You look at me, you look at my glasses, my beard, so you recognize me, right? So there are certain features. So everyone has unique face. That is at many features which come together. So at molecular level also, we have certain species or certain sequences, if it's DNA, certain amino acids, if it's a protein, which we know that we want to detect. So we need to make something complementary to that and put it on our device. For example, this I showed you last time. So what was happening here, that you put these green thing on the surface, like this DNA molecule, it's supposed to detect the red sequence, which is shown here on the top, on the upper side of that in the thing. And then there is, in this case, then there was a gold nanoparticle that would come in, like here, that will amplify the detection of this sequence. So the green thing here is the molecular recognition element. We call them MREs. Not the ones which we use in military, but the one which we would use to detect a specific molecule, molecular recognition element. And these are the things which you would put on the surface. Like in this case, we have put a molecule to detect these free floating molecules. So we hope that if they would complementary, they would bind them and we would see some change in current. So there's so many examples. Of course, you guys have seen those in literature review. So all of the devices that make claim of detecting something, they have to be functionalized to achieve their recognition part. And then you have transduction of signal and display of signal, which comes after. Here, for example, they show this surface which has a submolecule, this black colored molecule, which has been functionalized on the surface, right? With red linking unit. And then you bring your, this is AFM basically, a conducting AFM. So they are seeing the charge transport between this black molecule. But in all these cases, wherever they are doing a recognition, they have to place a molecular recognition element, a molecule, to do the detection. So I'm just showing the places where they would want to put them so they can detect. So what do we want to detect? In a sensor, in a biosensor or any kind of sensor, we want to detect certain things and we want to report them. The recognition is the most important thing, because if you get the recognition part right, then the sensor is meaningful. If the sensor is going to go off for every gas, for example, if it's supposed to be a sensor for toxic gas, and if it is going off for oxygen, nitrogen, hydrogen, that's not a meaningful sensor. That's like a joke, right? So, and we don't want to talk politics, but yeah, you can think of many people who would go off on things that don't matter. So it has to be recognizing part. And then you have to have a transduction element. We talked about this, that it can be ultimately an electrical meter, a light, a horn, a gong, whatever we want to do. A voltage change, a current spike, whatever it is, that has to be transferred. What kind of targets we are interested in? We are interested in molecules, we are interested in complexes maybe. We are interested in the whole cell maybe, right? So we talk about molecules, can be a gene, can be protein. We talk about complexes, it may be an enzyme which does some reaction. It may be the whole disease cell, cancer cell, for example. Now, they come in many forms, toxins, hormones, drugs, neurotransmitter, pathogens, metabolites. I wrote some things. I apologize, my writing on computer comes out bad, but that's why I'm speaking, right? So there's a whole bunch of molecules. And how we sense them, we can use some molecules to sense them. We can use some complexes to sense them. Or we can use a whole cell to sense another cell as well. And then there are specific examples. If we talk about molecules, yeah, protein, DNA, RNA, things that bind to very specific things. Lipid, sugar, amino acid, or if you take complex, maybe a virus, because virus has a capability to target a host. We can take its capability to target a host, and that can be used as a sensing itself. We can use it to even deliver a payload to a cell of whatever maybe you want to deliver. Again, these are some examples of element. Bacteria, that's another way how you can do that. But if you bring all these things together graphically, you can say that we have these parts where we do the recognition, we do transduction, put it in a detector, give a signal to end user. That would make up the whole a biosensor. Now, let's look at the specific parts of it. Recognition. When you say recognition, how does it occur? There are chemicals, there are molecules that selectively bind to things. They may be doing this, maybe they have like DNA where A binds to T and G binds to C. They may have a certain sequence that binds that you can clearly see. There may be a reason that we don't see or we don't know, but we just know they bind. So in nature, there are many things still where we don't completely know how do they bind, but we know they bind. So we can use those things. If you talk about, it says lock and key model. So that's the thing where we know, and you saw in that video of inner working of cell, there are things that bind. And I think Amara had in her KPR a nice example where things bind specifically. So we call them lock and key mechanism. When this happens, there is some other activity happens. Maybe the molecule release something or there is some movement, or whatever it happens. So that can be the uh, transduction of that thing, of that binding, of that recognition. Now, the recognition, if it happens at molecular level, we can define it. Maybe it's a detection of another molecule by a molecule, maybe it's detection of by a cell, maybe it's detection of a cell by a cell. Or, so there can be many designs. That's where the engineering part comes in, right? So if biologists can know things that react in test tube, right? But we can use them to convert it into a sensor, right? That's where a device comes in. That's where the Nano-Bio potential comes in. That we take, and many times you have seen in papers they show them by graphical shapes. A triangle would be going into a triangular shape. A circle would be going into a circular shape. So we depict these things with these cartoons just to make it a little bit easy. Now, there's a concept that when you have a surface, maybe a device surface, maybe silicon chip surface, you have to clean it, you have to prepare it. So we call these things as smart surfaces or clean surfaces. There are different ways how we explain them, but these are some terminologies that have become common, that we uh, take a surface, we put the molecule. Now, in this case, when we are using it for molecular recognition, we call it probe molecule because it's going to probe the sample that comes in contact with it, and it's going to bind to whatever it can recognize. So these probe molecules need to be carefully placed on the surface because there are issues, what we call as nano-bio interface issues. There are forces acting at that small scale which are much more dominant. There are charges at that scale which can disrupt the structure of a molecule. There are the how close you pack them, that they don't interfere with each other becomes important. So the end goal is we want to have a stable and robust interface that can reproducibly bind to a biomolecule. And we use these terms like which we would use in the maybe when you catch a thief, right? We interrogate, we try to find information. They interrogate, they bind to whatever comes in contact until they can uh, recognize it, right? So before we put it down, uh, before we come up with the final, there are lots of characterization that goes into to make sure the binding is specific. And we need to know exactly what is the sensitivity of the sensor. How small of an amount can it measure, below which amount it will be useless, or how high amount can it measure, because maybe above that amount it would get saturated. So you will not be getting a, a clear value of how much is something in a sample. So we do lots of characterization that goes in there. So biological molecules, put down again the whole list that we had in previous slide. Nucleic acids, proteins, antibodies is A, capital A with the B is for antibodies. And for what we do bioassembly. So we prepare these surfaces so we can put assemble molecules. We can measure, we can make maybe patterns, or maybe we want to make a surface reactive. There are the whole reasons why we do. Now, once you do that, there are certain properties that we measure to make sure there is some change that has happened on the surface. We cannot see these molecules exactly, not a whole lot of, because it's such a very small layer. Many times we can't even put them in, we can't even see them in microscope. They are such a small layer of those things, really nanoscale. So we have come up with many interesting characterization technologies or techniques that we do that. So to measure the surface quality, we use, maybe we measure reaction to see if the layer that you wanted to put there is there or not. Maybe sometimes the surface hydrophobic properties change. So hydrophobic property is where you put down a droplet and it, does it stay a droplet or does it spread? So that difference in droplet angle is measured. So and that gives us uh, wettability. Is it going to get wet or is it not getting wet? So that's a measure of hydrophobic or hydrophilic surfaces. We can we can see its reactivity if it changes, because if you have very small material put on a surface, that may react faster than a bulk material. The concept of surface to volume ratio, which we talked about before. Is it chemically reactive? Is there any mechanical change? Can you dissolve it? If it can let water flow through, is it, so there is, you can measure even conductivity. Put two electrodes and see if the surface has changed conductivity, higher conductivity, lower conductivity. So there are many ways where we can indirectly or directly measure the surface quality. There's, you can put it in a corrosive material and see if, because if there is a thin layer, that should be protecting the material that's below. That should change the corrosion properties. That would, if you put it into some wear or friction environment, those properties may change because of that surface functionalization. Biocompatibility, this is especially done for things which are implanted, right? So we need to, like titanium or other metals, so they get coatings of biocompatible materials. So before you do that, we have to put them maybe in a cellular environment to see if cells are happy with them or cells grow on those things. So many different techniques are used to measure or quantify the quality of a surface, of a functionalized surface. Now, during surface functionalization, our goal is to introduce chemical groups on the surface, right? Most of the time, it may be multiple levels of chemicals that are introduced. So for each level, we have to measure, but so when you do surface functionalization, we try not to change the bulk property. Because for example, if you put it on silicon, we don't want to change silicon itself, but we want to change the silicon molecules on the surface, silicon atoms on the surface, to be able to build our molecular structure or molecular kingdom or whatever you call it on top of that. Why we don't want to change the bulk? Because if you change the bulk, then we are messing with the electrical properties of the underlying material. We may be changing the mechanical properties of the underlying material, which means that now if you build something on top, you don't have a baseline left. You can use a bare silicon, for example, to use as a baseline to see the difference of molecules that we put on top, right? So that's why we normally do not want to mess with the bulk material itself. And when you put all the kingdom of molecules on top, we may be using self-assembled monolayers. That's what is called SAM. We may be using polymer layers, or we may be depositing things from a plasma. These are three ways how we can do that. So SAM is that you take a long chain of molecules and you make one side to be bindable to the surface, so the other side can be available for whatever reaction we want to do. And that molecule may be a carbon chain with the X functional group on one side and Y functional group on the other side. That's what we mean by CH2N on this slide. Or polymer layers, long molecules, we put the polymers coating on the surface. Or we do a thing called plasma polymerization. So plasma is ionized gases. If you create a chamber and apply power to it, that can that can convert the gas into plasma, and that plasma can have radicals, ions, which can be then deposited on a surface, and they can create a layer of monomers, single ionized entities that can gather on the surface and create a very uniform layer. So this is something which is done to create very good coating of, especially when the surface is uneven, to put a plasma polymerase layer on the surface. All right, so far with me? All right, so surface functionalization, what do we put down on surface? It can be a DNA molecule, it can be a protein, right? So here's the general scheme. There are four basic parts to it. You have the substrate, which can be silicon, silicon dioxide, gold, mica, glass, whole bunch of things. Then you make a passivation layer on top of that, which is shown as a gray color, right? And then you may have a linker molecule, which is shown a big circle, which anchors to the surface. And that can have your ultimate molecule that needs to go on top. So this is just an example of DNA molecule that we want to put down there, and DNA sensors have been shown to measure temperature, humidity, gases, even just the change of the molecule, right? Like in case of uh, DNA chips that we talk about some other lecture. So we put this linker molecule at the end of the DNA, which can bind to the surface itself. So we can do it directly or we can do indirectly. So these are the two, three ways how you do that. If you have a direct binding, then what you do, you take the DNA molecule and modify the DNA molecule itself. This is an example given here. So this word oligo here, oligo is, we call DNA as oligomers. So this, we buy them with this whole extension bound to it. And this extension can directly bind to a surface, like in this case, right? So, but the surface needs to have hydroxyl groups, OH groups, water vapors on the surface. So this can then do some reaction with this guy and bind to the surface. So we, here it says we use secondary amine to create this kind of monolayer and it binds to the surface. Yeah, the takeaway message is we can do direct attachment or we can use a linker molecule and use that linker molecule then to bind to a DNA. So in this case, the DNA or what we call oligos, hold on. So this is DNA molecule and then you have this intermediary molecule which has a benzene ring. So that's binding on this side and that's binding on this side. So you can create this monolayer by using a linker in between. So all these considerations come because we they change by what is the complexity of molecule or what is the interaction on the surface that we want or what are the changes that we want on the surface. So that would define what kind of surface functionalization technique we would use, right? Now, once you put them down, we have to then uh, do the measurement to make sure uh, they are doing the reaction they were supposed to do. So we have a bunch of techniques to do that also. We can measure the orientation of the molecule on the surface. We can measure the reactivity. Let me change color. It's the same color. Not a good end. We can measure the orientation of the molecule on the surface. This thing called FTIR. There's a machine that we use to measure orientation. We can put it in some reaction with some other chemicals and we can measure the reactivity. We can bend it and see if it forms any cracks on the surface to see if it's doing what it's supposed to do. We can do hydrophilic measurement, which was like putting a drop of molecule and seeing how it changes. There's another thing called ellipsometry, which looks at the reflected light and see if there is a change in the phase of the light, because there would be change in the refractive index, so that can change the phase of the light. So it can measure difference between the incident light and the phase of the reflected light and tell us if something changed there or not. There's another thing called XPS, X-ray photon spectroscopy, which again looks at the change in the uh, X-rays and their change in the phase of those. FTR is repeated here. We can put some fluorescent molecule which gives out light. That can be measured as an indicator of uh, what has happened on the surface. There is this thing showing here what says every bond has some vibration in it. Two carbon atoms have some vibration that goes on between them. That vibration is different if those carbon atoms are lying on the surface or if they are standing on the surface. We can measure even that as well. The vibration signal of a bond between two atoms. That can also tell us how those atoms are on the surface. If they are lying, if they are, we can find exact orientation of those on the surface. So that's another way how we can characterize our surface or functionalized surface or clean surface.